Welcome to our bioprocess engineering online tutorial on how to construct a microbial fermentation simulation model on a spreadsheet. Through the bioprocess engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. You also learn how to use spreadsheet software for key bioprocess engineering tasks, including analyzing experimental results, modeling and simulating bioreactors, designing and optimizing bioprocesses, evaluating economic and environmental performance. In the present tutorial, utilizing experimentally measured microbial growth kinetics, you will learn how to use a spreadsheet to construct a simulation model of the microbial growth. Step by step, you select the kinetic laws of microbial growth and metabolism. Using mass balances, you establish the differential equations describing the time variations of the medium composition. You numerically integrate the simulation model equations. And finally, you identify the model kinetic parameters. The modeling methodology is illustrated on the aerobic production of baker's yeast on sugar. The Saccharomyces cerevisiae, baker's yeast, is grown in a stirred aerated laboratory fermenter containing 1 liter of medium at a controlled temperature of 30 degrees Celsius. The medium contains an initial 50 grams per liter glucose concentration. The fermentation is started by an initial yeast inoculation at the concentration of 1 gram per liter. The fermenter is continuously aerated and stirred to avoid oxygen limitations. During the fermentation, medium samples are taken at increasing times. They are analyzed for the concentrations in grams per liter of glucose, ethanol, and dry weight yeast biomass. At an initial 50 grams per liter glucose, the yeast growth takes place over a 10 hours period. The glucose concentration decreases first slowly, then more rapidly until complete consumption. Simultaneously, the yeast concentration first increases slowly during the 2 to 3 hours lag phase, then exponentially until reaching a maximal near 7.5 grams per liter value. During the whole fermentation duration, ethanol is excreted concomitantly to the yeast growth. The final ethanol concentration is around 14 grams per liter. The growth-associated ethanol excretion by the yeast cells under aerobic conditions is the overflow of the excess glucose flux through the glycolysis pathway, known as the Crabtree effect. The initial latency phase of yeast fermentation is conceptualized by assuming that, initially, the inoculated cells reside in a latent state characterized by minimal sugar consumption and growth rate. These latent cells X-lat gradually transition into actively growing cells Xg. The measured cell concentration X is the sum of the latent cells and growing cells concentrations. The volumetric transition rate, denoted as R-lat third, measured in grams of cells per liter per hour, is assumed to be proportional to the concentration of latent cells X-lat, with K-lat representing the first-order transition rate constant. The value of K-lat determines the duration of the latency phase. A higher K-lat results in a shorter latency phase. For the growing yeast cells, the characteristic specific rates are the specific rate of yeast growth mu, in grams cells produced per gram cells an hour, the specific rate of glucose consumption, Q-glu, in grams glucose consumed per gram cells an hour, and the specific rate of ethanol production, QF, in grams ethanol produced per gram cell an hour. During the yeast batch fermentation, these specific rates are not constant. They can vary with the concentrations of the sugar and possibly of the excreted ethanol metabolite in the medium. The yeast kinetic laws express the influence of the substrates and metabolite concentrations on the yeast-specific rates. The growing yeast cells are characterized by the following kinetic laws. The specific growth rate follows a monads type of relation as a function of the glucose concentration. It is expressed as the product of the maximum growth rate by a glucose limiting term. Mu equals mu max glu divided by K glu plus glu. The growth-associated ethanol production rate, Qeth, is simply taken proportional to the specific growth rate. Qeth equals Yeth over X mu. The proportionality constant is the stoichiometric coefficient Yeth over X in grams ethanol produced per gram cells produced. Specific glucose consumption rate Q-glu entails two terms, one proportional to the cell-specific growth rate, the other proportional to the ethanol production rate. Q-glu equals Y-glu over X mu plus Y-glu over Eth Qeth. The two proportionality constants are the stoichiometric coefficient Y-glu over X in grams glucose consumed per gram biomass produced, and the stoichiometric coefficient Y-glu over X in grams glucose consumed per gram ethanol produced. After formulating the kinetic laws governing yeast growth, the subsequent task involves establishing the differential equations that depict the temporal changes of the biomass, ethanol, and glucose concentrations. These equations are derived by writing the instantaneous mass balances for the fermentation compounds. For a component, the instantaneous mass balance that expresses the fundamental principle of mass conservation at each instant involves four terms: the inlet rate from the outside to the inside of the fermenter, the outlet rate from the inside to the outside of the fermenter, the biotransformation rate that can be a production rate for a product or a consumption rate for a substrate, and the internal variation rate that represents the rate of the component's mass variation inside the fermenter. The instantaneous mass balance relation is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced biomass and ethanol, negative for the consumed glucose. For a batch fermentation, there are no inlet rate and outlet rate terms, and the instantaneous balance simplifies to plus or minus production rate equals variation rate. For the latent yeast cells, the instantaneous balance, in gram cells per hour, on the whole fermentation medium writes minus R lat equals dmx lat over dt, where R lat is the yeast transition rate from latent to growing cells, and mx lat the mass of latent cells. Introducing the medium volume V and the specific latency constant K lat, the balance relation becomes K lat x lat V equals V dx lat over dt. Accordingly, the differential equation describing the time variation of the latent yeast cell concentration is dx lat over dt equals minus K lat x lat. For the growing yeast cells that are produced both by transition from latent cells and by growth, the instantaneous balance in gram cells per hour on the whole fermentation medium writes R lat plus Rx equals dmxg over dt, where Rx is the yeast growth rate and mxg the mass of growing cells. Introducing the medium volume V and the specific growth rate mu, the balance relation becomes Ki lat x lat vi plus mu xgv equals V dxg over dt. Thus, the differential equation describing the time variation of the growing yeast cell's concentration is dxg over dt equals K lat x lat plus mu xg. For the produced ethanol, the instantaneous balance in grams of ethanol per hour on the whole fermentation medium is Reth equals dmeth over dt. Reth is the ethanol production rate, and meth the ethanol mass. Introducing the specific ethanol production rate Qeth, the balance becomes Qeth xgv equals deth over dt. Accordingly, The differential equation describing the time variation of the ethanol concentration, eth, is deth over dt equals qeth xg. For the consumed glucose, the instantaneous balance in grams glucose per hour is minus R glu equals dm glu over dt. R glu is the glucose consumption rate and m glu the glucose mass. Introducing the specific glucose consumption rate Q glu, the balance becomes minus Q glu xgv equals Vd glu over dt. And the differential equation describing the time variation of the glucose concentration is d glu over dt equals minus Q glu xg. In summary, the constructed simulation model of the yeast growth in the batch fermenter entails the instantaneous mass balances for the fermentation components and the postulated kinetics laws of yeast growth, ethanol production, and glucose consumption. The measured yeast concentration X is the sum of the latent X lat and growing cells Xg. When the kinetic laws are introduced in the mass balances relations, one obtains the set of differential equations representing the time variations of the yeast, ethanol, and glucose concentrations during the batch fermentation, starting from the initial glucose concentrations GLU0 and latent cells concentration XLAT0. The subsequent phase in the fermentation modeling process involves integrating the derived set of differential equations. These equations depict, at any given moment, the derivatives or the rates of change over time of the yeast, ethanol, and glucose concentrations. Mathematically integrating these differential equations yields the temporal evolution of the concentrations. On spreadsheets, differential equations are easily integrated, whatever their mathematical complexity, using numerical methods. The numerical integration approximates the actual solution curve by a polygonal curve made of successive points and straight line segments. Let's consider the general differential equation describing the time variation of the concentration, dC over dt equals a function of C and T. The differential equation is transformed into a finite difference equation by dividing the timescale t into incremental time steps of length delta t. The derivative dC over dt is then approximated by the ratio of the concentration variation delta C to the time step delta t. And the differential equation then becomes delta C over delta t equals A, or delta C equals A delta t. The incremental concentration variation delta C is the difference between the concentration Ct plus delta t at time t plus delta t and Ct at time t. The resulting finite difference equation is Ct plus delta t equals Ct plus At delta t. At is the slope at time t of the concentration time variation. Mathematically, this relation represents the first-order development of the concentration function with respect to time. The difference relation between the concentrations at time t and t plus delta t is used in the following way to carry out the numerical integration. The integration is started from the initial concentration C0. The slope A0 is calculated at time 0, and the concentration C1 at the following time T1 is determined by adding to C0 the concentration increment A0 delta T. At time T1, the slope A1 is then recalculated, and the concentration C2 at the following time T2 is determined as C1 plus A1 delta T. The procedure is repeated to calculate C3 and the following concentrations over the whole investigated time period. The differential equations previously established for the yeast growth fermentation are numerically integrated using the following incremental relations. For the latent yeast cells, x lat at t plus delta t equals x lat at t minus k lat x lat at t delta t. For the growing yeast cells, xg at T plus delta T equals xg at T plus k lat, x lat at T, delta T plus mu T, xg at T, delta T. For ethanol, eth at T plus delta T equals eth at T plus q eth T, xg at T, delta T. And for glucose, glu at T plus delta T equals glu at T minus q glu T, xg at T, delta T. The yeast growth modeling is carried out on a spreadsheet containing the following sections: the experimental results table with the measured cell, ethanol, and glucose concentrations during the batch fermentation. The graphs representing the experimental and simulated concentrations, time variations, the kinetic parameters section, the initial conditions section, and the numerical integration table. In the kinetic parameters section, you enter initially assumed values for the parameters of the postulated yeast kinetic laws. They are obtained from experimental results analysis or from literature. Introduced values are, for example, 0.25 hour minus 1 for mu max, 1 gram per liter for Ks, 2 gram ethanol per gram, biomass for Y eth over X, 2 gram glucose per gram biomass for Y glu over X, 2 gram glucose per gram ethanol for Y glu over eth, and 0.2 hour minus 1 for K lat. In the initial conditions section, you enter the initial glucose concentration of 50 grams per liter and the initial yeast biomass concentration of 1 gram per liter. The differential equations integration is carried out in the numerical integration table that calculates the concentrations and specific rates at increasing times. The first line of the table contains the initial concentrations of the fermentation components. It is completed in the following way. Set the time increment delta T at 0.1 hour. Set the initial time T at 0. Transfer the initial latent cell concentration of 1 gram per liter from the initial conditions section. Set the initial growing yeast concentration at 0. Calculate the total yeast cells concentration X as the sum of X lat and Xg. Set the initial ethanol concentration at 0. Transfer the initial glucose concentration of 50 grams per liter from the initial conditions section. The first line of the integration table also calculates the growing yeast-specific rates. It is completed in the following way. Calculate the specific growth rate by its kinetic law as a function of the glucose concentration, mu equals mu max glu divided by k glu plus glu. The two parameters, mu max and k glu, are transferred from the kinetic parameters section. Calculate the specific ethanol production rate by its kinetic law. Q eth equals y eth over x mu. The parameter y eth over x is transferred from the kinetic parameters section. Calculate the specific glucose consumption rate by its kinetic law. Q glu equals y glu over x mu plus y glu over eth q eth. The two parameters y glu over x and y glu over eth are transferred from the kinetic parameters section. In the second line of the integration table, the concentrations are calculated at the first incremental time delta T using the numerical integration relationships. Set the delta T equal to the previous line delta T. Calculate the time as the time at the previous line plus the time increment delta T. Calculate x lat by the relation x lat at the preceding time minus k lat transferred from the kinetic parameters section x lat at the preceding line delta T. Calculate xg by the relation xg at the preceding time plus k lat x lat at the preceding time delta T plus mu at the previous time xg at the preceding time, delta T. Copy-paste the formula of the preceding line to calculate the total yeast cell concentration X. Calculate ETH by the relation ETH at the preceding time plus QETH at the previous time, XG at the preceding time, delta T. Calculate glue by the relation glue at the preceding time minus Q glue at the previous time, XG at the preceding time, delta T. To complete the second line, copy-paste the first line formulas of the yeast-specific rates in order to calculate the specific rates of growth, ethanol production, and glucose consumption at the first incremental time delta T. In the previous kinetic loss formula, the kinetic parameters must be set as constants. The final step of the numerical integration is to copy-paste the whole second line down to the final time of 10 hours. This yields the time variations of the concentrations during the whole batch fermentation. The results of the numerical integration are presented in the 3 graphs at the top of the spreadsheet, alongside the experimental results. For the initially assumed kinetic parameters, the shapes of the temporal variation curves for yeast, ethanol, and glucose concentrations are correct. However, the values obtained differ substantially from the experimental data, with the modeled yeast growth being slower than what was measured experimentally. The final task of the modeling is to identify the investigated yeast kinetic parameters to achieve the best fit between the experimental data and the model predictions. Since the modeled latency phase is longer than what is experimentally observed, the first parameter to adjust is the latency constant, kRlat. Indeed, increasing kLat from 0.2 to 0.6 hour minus 1 yields a much better modeling of the yeast growth kinetics. An additional slight increase in the maximal growth rate mu max from 0.25 to 0.27 hour minus 1 yields an excellent fit between the simulated and experimental yeast growth curves. Furthermore, the ethanol and glucose concentrations temporal variations are best modeled by adjusting the stoichiometry coefficients of the investigated yeast strain, YEth over X, to 2.1 grams ethanol per gram yeast, Y glu over X to 2.1 grams glucose per gram yeast, and Y glu over ETH to 2.6 grams glucose per gram ethanol. In this tutorial, you learned how to use a spreadsheet to construct a simulation model of the aerobic baker's yeast growth on sugar. Step by step, you select the kinetic laws of yeast growth and metabolism. Using instantaneous mass balances, you establish the differential equations, describing the time variations of the sugar, yeast, and ethanol concentrations. You numerically integrate the simulation model equations. And finally, you identify the kinetic parameters of the yeast strain. If interested, you can gain a deeper insight in microbial fermentations by enrolling to one of our 2 online courses, Microbial Fermentation Processes, Optimize Fermenters Operations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.